Hello friends, welcome back to my channel. I hope you are happy and healthy and enjoying your life. In the last video, we had discussed about heat dissipation from the infinite long fin, that is when L tends to infinite. What is the temperature variation and what is the heat dissipation from the fin that we had discussed. And based on that, we had solved some problems and some were given to you as an assignment. Now, in the today's video, we are going to discuss about heat transfer by conduction part 9. So still we are discussing about steady state heat transfer, in which we are discussing about extended surfaces or fin, and in this we are going to discuss about the next case, that is second case. So friend, in this video we are going to discuss about heat dissipation from the fin insulated at the tip. It means that when the fin is insulated at the tip, means there is no temperature gradient at fin tip, or the temperature gradient at fin tip, that is dt by dx, is 0. So we are going to discuss about derivation of formula related to temperature variation in the fin which is insulated at the tip, plus what is the heat dissipation from the fin when that is insulated at the tip, and based on that we are going to solve some problems which is helpful to you for your examination, that include UPSC, that is IES, or your regular engineering examination. So friend, now we have to discuss about heat dissipation from the fin which is insulated at the tip. So here figure number 23 you can see where the hot surface is available at T0 temperature, and at T0 temperature the fin is attached. The fin is of finite length and the tip of the fin is insulated. So as we know from the previous case that at x equals to 0 the temperature is equals to T0. If you want to know in detail about these extended surfaces, the links were given in the description box. You can refer that link, and based on that you will get what are the boundary conditions which we have to apply to find out heat dissipation and temperature variation in this case. So when x equals to 0, at that time temperature is equals to T0, that is known to us. And now the second condition is available with us, that is when x equals to L. At that time dt by dx is 0, because when the tip is insulated no temperature variation is observed in this case. So the top part is talking about fin and the bottom part is talking about temperature variation along the length of the finite fin. So now we try to find out what is the temperature variation formula and what is the heat dissipation in this case. So now for present case we are with two boundary conditions. First is when x equals to 0, theta equals to theta 0, and second condition is when x equals to L, dt by dx is 0. So from the most general equation we know that theta, that is equals to c1 e raised to mx plus c2 e raised to minus mx. When we apply first boundary condition we will get theta 0, that is equals to c1 plus c2. Now when we want to apply second boundary condition, first we have to find out what is the value of dt by dx. So we have to go for the most general equation, that is theta, that is equals to temperature gradient, that is T minus Ta, that is equals to C1 e raised to mx plus C2 e raised to minus mx. So we have to differentiate this equation with reference to x. So we will get value of dt by dx, and to put the boundary condition for the second case we have to put dt by dx, that is equals to 0. So we will find out what answer we will get. What is the dt by dx value and what is happening when we will put dt by dx, that is equals to 0 in this case. So friend, you can see when dt by dx at x equals to L, that is equals to 0, we will get m1 into c1 into e raised to ml minus m2 in m into c2 into e raised to minus ml. So you can say c1 into e raised to ml minus c2 into e raised to minus ml, that is equals to 0. So two equations are available with us, and when we will solve this equation 1 and 2, we will get the value of C1 and C2. So you can see by solving we will get C1, that is theta 0 into e raised to minus ml divided by e raised to ml plus e raised to minus ml, and the value of C2, that is equals to theta 0 minus C1, that is the bottommost line, and the value of C1 is available on the second line from the bottom. So the constant values C1 and C2 are available, and now we have to put that values in the most general equation to find out what is the temperature variation. So we'll go with the next step. I hope this is very much clear to you. We'll go ahead with this solution. So friend, you can see the value of C1 and value of C2 that is available in the form of equation number C and D. And now we have to put the value of C1 and C2 into the most general equation. So you can see when we put the value of C1 and C2, we will get theta, that is equals to theta 0 into square bracket, we will get e raised to minus ml divided by e raised to ml plus e raised to minus ml bracket complete into e raised to mx plus theta 0 into square bracket e raised to ml divided by e raised to ml plus e raised to minus ml square bracket complete into e raised to minus mx. So theta 0 is common from both the side. So we can say that theta divided by theta 0, that is equals to e raised to m into L minus x plus e raised to minus m into L minus x divided by e raised to ml plus e raised to minus ml. So I can rewrite theta by theta 0 as t minus ta divided by t0 minus ta, that is equals to cos h hyperbolic function cos hyperbolic into bracket m into L minus x bracket complete divided by cos h. This h is not a convection heat transfer coefficient. This is hyperbolic function. In some of the calculator HYP is mentioned, that is hyperbolic function, divided by cos hyperbolic m into L. So this equation E which is available, that is indicating the temperature variation for a fin which is of finite length and the tip of the fin is insulated, where cos hyperbolic m into L minus x, that is equals to e raised to m into L minus x plus e raised to minus m into L minus x divided by 2, and cos hyperbolic ml, that is equals to e raised to ml plus e raised to minus ml whole divided by 2. So from these two equations available from the maths, we will get temperature variation in dimensionless form, and that is cos hyperbolic m into L minus x divided by cos hyperbolic ml, that is the temperature variation which we will get for the finite length of fin with insulated tip. So friend, I hope this is very much clear to you how this equation is derived, and this will be helpful to us when we are going to solve the problem related to industry or when that is available with the real life. So now our second task is to find out heat dissipation from the fin. So at the base, what is the heat dissipation that we have to find out? So as per Fourier's law, we know that Q fin, that is equals to minus Ka dt by dx. So we can write minus K into cross section area into dt by dx at x equals to 0. So our first target is to find out what is the value of dt by dx when x equals to 0, that is at base. So we know that T minus Ta divided by T0 minus Ta, that is equals to cos hyperbolic m into L minus x divided by cos hyperbolic m into L. So this T minus Ta is available, so we have to go for differentiation of above equation, and in that equation we have to put the value of x, that is equals to 0. So now friend, this is a pure mathematics. When we'll go for differentiation and when we'll put x equals to 0 value, we will get dt by dx at x equals to 0, that is equals to minus m into T0 minus Ta into tan hyperbolic m into L, where T0 is the base temperature, Ta that is ambient temperature, m that is the fin constant, L that is the length of fin, and tan h that stands for tan hyperbolic function. So now when we'll put this value in the equation of Q fin, we will get Q fin that is equals to K into cross section area into M into T0 minus Ta into tan hyperbolic m into L. So upon simplification we will get the equation G, that is Q fin, that is equals to under root of P H cross section area into K into bracket T0 minus Ta into tan hyperbolic m into L, where P is the parameter of the fin, H is the convection heat transfer coefficient of surrounding fluid, cross section area is a cross area of fin, K that is the thermal conductivity of fin material, T0 is the base temperature, Ta that is ambient temperature, tan H that is the tan hyperbolic function, m is the fin constant, and L is the length of fin. So this equation G and the previous equation E, these two are the required equation which is talking about heat dissipation and temperature variation along the fin, which is of finite length and the tip of the fin is insulated. So I hope the derivation is very much clear to you, and now based on this derivation we have to go for solution of some problem related to industry or related to real situation. So friend, the data is available. A steel rod, thermal conductivity 54 watt per meter Kelvin, with a cross section of an equilateral triangle, each side is of 5 mm, is 80 mm long. It is attached to the furnace wall, which is maintained at the temperature 400 degrees Celsius. The surrounding is at 50 degrees Celsius and the surface conduction is 90 watt per meter square Kelvin. Calculate the heat dissipated by the rod. Assume the tip of the fin is insulated. So friend, in this data, how to identify the problem, that is a very big question. So you can see here in the data itself, it is clearly given that the tip of the fin is insulated, and very important thing which you can see here is the total length of fin is given. So the situation is very much clear to you, that is fin is of finite length and the tip of the fin is insulated. So the steel rod is given with the thermal conductivity, cross section area is given, equilateral triangle with the side dimensions are given, length of the fin is given, it is attached with the furnace, and what is the furnace temperature, that is also given, surrounding temperature is given, convection heat transfer is given. Just we have to find out what is the heat dissipation Q from the fin. So now let's solve the problem. So friend, this figure is the pictorial representation of the data. The cross section is a triangular with the side dimension A, length is L, surrounding temperature is Ta, base temperature is T0, and now we try to solve the problem. So when this kind of numerical is asked, first you try to plot what is given to you, what you have to find out. So now friend, the formula is known to us, Q that is equals to K into cross section area into M into T0 minus Ta into tan hyperbolic M into L. Or you can use the formula under root of PHAK into T0 minus TA into 10 hyperbolic ml. So here first we have to find out what is the Fin constant m, what is the perimeter, what is the cross section area. So you can see the value of m, that is Fin constant, that is under root of pH divided by AK, where P is the perimeter and that value is 3A. Cross section area, that is 1/2 A into under root of 3 by 2A, that is under root of 3 by 2A square. So when we'll put all the values of thermal conductivity, convection heat transfer coefficient and the value of A, that is the side dimension 5 mm, we will get the value of m, that is Fin constant, that is equals to 48.06 meter inverse. And when we'll put the value of m, perimeter, cross section area, thermal conductivity and convection heat transfer coefficient in the formula of heat dissipation for the finite length fin with tip insulated, we will get the value of Q, that is 9.82 watt. Very important thing is, don't confused with convection heat transfer coefficient H and hyperbolic function H. So I hope the answer is very much clear to you and I hope you are getting this answer. Let's go for the next numerical now. So the data for next problem is, Fin is provided to increase the heat transfer rate from the furnace wall. Which of the following arrangement will give higher heat transfer rate? Take T0, that is 230 degrees Celsius. The first arrangement is 6 fins of 10 centimeter length and second arrangement 12 fins of 5 centimeter length. Take thermal conductivity equals to 200 watt per meter Kelvin, convection heat transfer coefficient, that is equals to 20 watt per meter square Kelvin, cross section area of the fin, that is 2 centimeter square, perimeter of the fin, that is 4 centimeter, surrounding air temperature, that is TA, that is equals to 30 degrees Celsius. So we have to solve this problem, and out of these two situations, which situation is preferred, that we have to find out, and based on that we have to derive the conclusion. I hope friend this data is clear to you. Either we have to select case 1 where 6 number of fins are available with 10 centimeter length, or we have to go for 12 number of fins with 5 centimeter length. So let us try to solve this problem. So here the case is given with heat flow through n number of fins. So we can say Q, that is heat dissipation through the fin, that is equals to n into K into cross section area into fin constant m into T0 minus TA into 10 hyperbolic m into L. So the Fin constant m value, that is under root of pH divided by AK, and that value is 4.47 meter inverse, where we have to convert all the centimeters and millimeters into meter to find out the required answer. So the m value is available, that is 4.47 meter inverse. Now we will consider the first case, that is number of fins equals to 6 and the length is equals to 10 centimeter, that is 10 into 10 power minus 2 meter. So the perimeter is available 0.1 meter, m into L value that is calculated, and that value is 0.447. And based on that, when we will calculate the value of heat dissipation with case 1, that is Q1, we will get 89.99 watt. So friend, I hope it is very much clear to you. It is a very simple. Only you should take care that 10H, that stands for 10 hyperbolic function. And now we have to find out what is the value of Q2 when we will consider the second case. So for first case, the heat dissipation is 89.99 watt. Now we will go for the second case where 12 number of fins are there with the length 5 centimeter, that is 5 into 10 power minus 2 meter. And in that case, the value of m into L, that is 0.2235. And based on that, when we'll consider the heat dissipation Q2, that value you can see, friend, that is 94.34 watt. And based on that, we can see that when we'll go for the second arrangement, we'll get more amount of heat transfer or more amount of heat dissipation. So the purpose to use the fin is to dissipate more and more amount of heat from the system to surrounding, and hence we can conclude that we have to go for 12 number of fins with 5 centimeter long. I hope this is very much clear to you. Okay friends, in this video we had discussed about heat dissipation through a fin which is of finite length and the tip of the fin is insulated. We had derived the formula to find out temperature variation and heat dissipation from the fin which is of finite length. Also, we had solved two problems which are very much related to industrial application. So, if you like this channel, do not forget to subscribe this channel and share this channel among your friends. Take care. Have a nice day. Goodbye.